All right, this is lecture number 4 for discrete optimization. This is going to be about algorithms for computing maximum flows. So in the last lecture, we have looked at two different characterizations for maximum flows by augmenting paths and by minimum cuts. The one for by augmenting path is going to be important also for this algorithmic part. So we're going to look at three, but actually two different algorithms. The Ford-Fulkerson algorithm is a generic algorithm, and Edmonds-Karp is going to be a version of that with a polynomial computation time. And the preflow push algorithm is interesting to look at because it's a totally different algorithm that uses so-called preflows, and it has a very nice and elegant analysis. Okay, so let's start with the Ford-Fulkerson algorithm. And as a matter of fact, this algorithm is almost suggested by itself when you look at the characterization of maximum flows by augmenting paths, right? So since we know that we have a maximum flow if and only if there is no augmenting path in the residual network, we just try to find augmenting paths in the residual network. We send the corresponding flow along such an augmenting path, and we iterate that until we cannot find any augmenting path anymore. And that is exactly the algorithm by Ford and Fulkerson. So we start with a zero flow. And as long as we still find an augmenting path in the residual graph, we augment the flow along that path by the corresponding residual capacity of that path. We, of course, have to update the residual graph GF. And we iterate this thing as long as we can find augmenting paths, since we know as long as there still exist augmenting paths, the flow cannot be optimal. Okay. So when we exit this while loop, we know we have the optimality proof because there is no augmenting path anymore, and we can return the flow F being a maximum flow. Now let's assume, just for convenience, the graph is connected, so the number of edges is certainly at least n-1. Then I claim that finding an augmenting path in the residual graph in each iteration can be done in linear time. And linear time, since the graph is connected, can be written conveniently as order m. M is the number of edges. How do we do that? Well, it could be, we can use any so-called reachability algorithm. So for example, breadth first search in the graph, which is known to be a linear time algorithm. So I'm not sure if everybody knows what BFS or DFS stands for. So BFS stands for breadth first search. DFS stands for depth first search. And that's the two most basic reachability algorithms for graphs. And reachability here refers to the question, is the target vertex T actually reachable from the source vertex S? And let me just briefly explain what BFS is. So if you look at this picture, you can think of breadth first search as starting with a source vertex and then scanning the whole neighborhood of the source vertex and then scanning the neighborhood of the neighbors of the source vertex, etc., etc. So if you find by this process the target vertex T, you will have found an augmenting path because these edges here refer to edges in the residual graph. Now, if you ask how to implement that, I can answer that very quickly. You just take your implementation of Dijkstra's algorithm with the assumption that all the edge lengths are actually equal to 1. Okay. Then the distance label, the distance for vertex u refers or will be the minimum number of edges on any SU path if it exists. Okay. And thinking about computation time now, remember that the most expensive operation in Dijkstra's algorithm was that in each iteration we had to find the vertex among the unprocessed vertices with minimum label d of u. But this is now very easy because I can organize all these vertices in a so-called queue. And whenever I update a distance label, I put the corresponding vertex at the end of the queue. And at the top of the queue, I always find the vertex with a currently minimum distance label. Okay, so in the beginning, that would be the source vertex, which has distance label 0. and I process all the outgoing edges of the source vertex. And when I'm done with that, I would eliminate this one, and that one, vertex number 1, would be the next vertex to be scanned. Okay, so I remove the top element from the queue after having done or scanned all the outgoing edges. And this way, we find the vertex with minimum distance label just in constant time, and Dijkstra's algorithm will have a computation time which is just linear in the size of the graph, so order n plus m. So we have a linear time algorithm for finding augmenting paths in the corresponding residual graph. So we have a complete description of an algorithm for computing maximum flows, actually. And that is exactly the Ford-Fulkerson algorithm, right? As long as there exist augmenting paths in the residual graph, I augment the flow along these paths and I iterate until I find no more augmenting path. All right, so let's look at the analysis. So the first is the correctness proof. So the statement is as follows: when the Ford-Fulkerson algorithm terminates with flow F, then this flow F must be a maximum flow. And that is, of course, a direct consequence of our characterization, because when the algorithm actually terminates, there is no augmenting path in the corresponding residual graph. Hence, the flow must be maximal. Okay, nice. Let us have a brief outlook on what comes in one of the later lectures as well. Because what happens if the input to the problem is only integers? So that means all the edge capacities are integer numbers. Well, then, if all the capacities are actually integer numbers, I claim there exists an integer valued maximum flow. Why is that? Well, the Ford-Fulkerson algorithm actually computes it, right? Because we send flow along augmenting paths. By how much do we augment the flow? Well, that's the residual capacity of that augmenting path. And since all the capacities are integers, all the residual capacities will be integers. So we augment the flow in each iteration by an integer amount. So the Ford-Fulkerson algorithm actually computes an integer valued maximum flow. And does the algorithm also terminate? The answer is yes, because there is an upper bound on the maximum flow value. For instance, the total sum of all the capacities in the graph is certainly an upper bound on the maximum flow value. And in each iteration of the algorithm, we are sending an integer amount, so that is at least 1. So after a finite number of iterations, we will be done with a maximum, having computed a maximum flow. So in summary, the optimal flow value is bounded by some actually integer amount, and the Ford-Fulkerson algorithm augments the flow by at least +1 in each iteration, because each time we pick an augmenting path with residual capacity at least 1. Remember that the residual capacities or the residual edges only exist if the residual capacity is larger than 0, which in integers means at least 1 more, +1. And in each iteration, the Ford-Fulkerson algorithm only augments by integer amounts of flow, and therefore we will have computed an integer optimal solution. So this is a special case of finding even integer valued solutions to certain linear programs, which will be discussed also later on. So that is the correctness proof actually also for the case when we have integer capacities. So before we continue with the correctness of the algorithm, let's briefly look at the computation time. So first of all, we have linear computation time in each iteration. So in each iteration in which we find augmenting paths. So that is because we have to construct the corresponding residual graph once we have augmented the flow. And then we will have to compute the next augmenting path P. And both operations, construction of the residual graph and computation of an augmenting path in this residual graph, takes time, which is linear in the size of the graph. For example, using breadth first search for finding that augmenting path. Now, assuming that we have integer capacities, in each iteration the flow value increases by at least +1. So that means how many iterations do we actually need? Well, at most as many as the maximum flow value itself, right? Because in each iteration, we add at least +1 on the current flow value. So there is an upper bound on the computation time or the number of iterations, which is determined by the maximum flow value, F star here. Okay, F star would be a maximum flow. So that's at least a finite computation time, but it's not really good because this upper bound depends on the value of the flow, and the value of the flow could be much, much larger than, for example, the size of the network, right? We could have capacities in the order of millions, and then this computation time or this upper bound is no good. So that means the algorithm could be very slow when the maximum flow value is large, but there is even more that we can say, and that is even more severe. So first of all, our correctness proof was actually only valid because it depends on the fact that the algorithm terminates. Once the algorithm terminates, we have the correctness proof by the augmenting path theorem. But does the algorithm actually terminate? And the answer is not in general. It terminates certainly after a finite number of iterations for integer capacities, but not when the capacities are allowed to be arbitrary real values. I will show a little example in a second. But first, let's have a look at the computation time itself. So look at this little example here, where we have huge capacity. So that's 1 million on all these edges here. And how could the algorithm proceed on this small instance? Well, if we are unlucky, we find an augmenting path along this zigzag path here, which has a residual capacity of only 1, because this capacity here is 1 in the middle. So we augment by +1 in this direction. In the corresponding residual graph, we will have the arc in the opposite direction. And again, it will have a residual capacity of 1. So in the next iteration, we might find this augmenting path here. And we augment the flow by another value +1. So Ford-Falkerson actually would need, in the worst case, 2 million flow augmentations before we are done. So this is not very convincing, since this is a trivial instance, and what if we would have sent flow along these two augmenting paths, we would have been done after only 2 iterations. But as I said, it's even more severe that the algorithm may even fail to terminate at all. And not only that, it may even be that it computes the wrong or converges to the wrong value. So if the capacities are allowed to be arbitrary real numbers, the Ford-Falkerson algorithm may fail to terminate at all. So it would iterate forever, and each time augmenting smaller and smaller amounts of flow. And there you can even construct examples where it converges to the wrong value, so it does not even converge to the optimum flow value. And there is a paper where this is explained. That's a paper by Zwick from the mid-90s. So it's called the smallest network on which the Ford-Falkerson maximum flow procedure will fail to terminate. But it not only shows that the algorithm fails to terminate, it also shows that it converges to some value which is not equal to the maximum flow value. So if you want, you can have a look. So here's the whole example, but I'm not going to explain it. So this is the whole network. So it's really a small network, and you can convince yourself. So the augmenting paths are defined in such a way that the flow augmentations fulfill a certain linear recurrence relation. And then you can show, if you look down here, quite easily that the algorithm converges to a value equal to 3, whereas the maximum flow value could be much larger. Okay. So what do we have? Well, we have an algorithm, and we also have a correctness proof and a finite computation time for integer edge capacities, but not in general. And the question is how to fix this problem. So for real capacities, this algorithm is no good and even converges to the wrong value if we are unlucky. And the answer to fix this problem, the bug fix for this nasty behavior of the Ford-Fulkerson algorithm is quite simple. So of course, in this construction here, we were very unlucky in choosing the augmenting paths subsequently, right? So how to fix it on this particular example? Well, you could, for example, pick specific augmenting paths. So for example, one which has maximal residual capacity, or which has minimal number of edges. In this graph, that would work, right? So as a matter of fact, both bug fixes would work. And one of them is known as Edmonds-Karp algorithm. So Edmonds and Karp published a paper in '72 showing that when you always pick augmenting paths with minimal number of edges, then you can fix this problem and you get a correctness proof and a polynomial computation time, which only depends on the size of the graph, but not on the edge capacities. So that is what we look at next, the Edmonds-Karp algorithm. So conceptually, this is just the same algorithm as before, just the same as Ford and Fulkerson, only that we no longer pick some arbitrary augmenting path, but the shortest augmenting path. So this is the description of the algorithm, where we, in each iteration, pick a shortest augmenting path in the corresponding residual graph, and shortest here refers to the minimal number of edges among all augmenting paths P. So how do we get these shortest augmenting paths? You might wonder, okay, so how do I obtain shortest augmenting paths in the number of edges algorithmically? And the answer is quite simple. That's actually what BFS does for us. Because if you remember, breadth first search is an algorithm which kind of fans out from the source vertex and looks at all the neighbors and then looks at all the neighbors of the neighbors and so on and so on. And when we find the target node by using BFS, we will automatically have computed a shortest augmenting path in the corresponding residual graph, shortest with respect to the number of edges that it uses. Notice that in the literature, you might find other implementations or other descriptions of this Edmonds and Karp algorithm, but conceptually, this is the main idea. All right, so let's look at the analysis of this algorithm, because my claim was that this gives us an algorithm which does no longer depend on the maximum capacity or the maximum flow value. It will give us a polynomial computation time in the size of the graph, number of vertices and edges, and actually it will also work for arbitrary capacities. So the proof of all these claims follows by three lemmas. First lemma says, well, in each iteration of the algorithm, at least one edge will be removed from the corresponding residual graph. That is obvious because once we have computed a residual path, an augmenting path, we will send the maximum flow through it. So that means at least one edge of that path will get saturated. It may later come back in the residual graph if we find an augmenting path later on that uses this edge in the opposite direction. But in each iteration, at least one edge will be removed from the corresponding residual graph. So here's a picture that supports this claim. If we send the maximum amount of flow through such an augmenting path from S to T, there will be at least one edge which gets saturated. The next observation is that the distance labels, and here the distance labels refer to the current length of a shortest path from S to U. Okay, so D of U is the length of the shortest SU path, where the lengths of the edges are considered to be 1, so we are counting the number of edges only. Okay, so if these distance labels, we are looking at these distance labels throughout the iterations of the algorithm. So these distance labels are recomputed in each of these iterations because we have changed the residual graph. And the claim is when we do that, these distance labels are actually monotonically increasing, so they will never go down. And finally, the third observation is that each of the edges of the graph, if we focus on one fixed single edge, it may be removed a couple of times, because in each iteration at least one edge is removed from the corresponding residual graph. But how often can a single edge be removed? And I claim that this is only a linear number of times. It's actually n-1 divided by 2. So lemma 1 is clear and proved. Let us look at the proofs for the other two lemmas. So lemma 2 says, from iteration to iteration, the distances of the vertices from the source vertex S can only get larger. And if we show this is true for all the vertices from this augmenting path, then it will also be true for all the other vertices. And for all the vertices on this augmenting path here, let's consider the first vertex U, which obtains a new in edge, a new ingoing edge. Why does it obtain a new in edge? Well, because we were saturating an edge in that direction, and therefore in the corresponding residual graph, this might be a new edge that wasn't present before. So we have, because of the presence of this edge here from V to U, we might have a new path actually to reach vertex U. So clearly the removal of this saturated edge doesn't decrease any distance label. Removal of edges does not help to get shorter paths, but the introduction of this new residual edge in the new residual graph might decrease potentially some of the distance labels, in particular the one to this vertex U here. So VU is an edge that got added to the next residual graph. It's a backward edge on that path P. But by choice of U as the first vertex for which this happens, the new in edge does actually appear. We know that this path here to W also existed before. And we know that in that iteration, this was actually a shortest augmenting path in the number of edges. So the distance from S to U must be smaller or equal than the distance from S to W, because otherwise this would be another path to vertex V, which would be shorter than this one. But this one is actually a shortest SV path. And shortest here means in the number of edges. Therefore, all the labels are 1 here. Okay, so that is the argument. The distance label of W is larger or equal than the distance label of U because P was the shortest SV path before. So therefore, this new path actually does not decrease the distance label of U. So this we do not create any shorter SU path by introducing this backwards edge here. And then inductively along the path, the same is true for all the other vertices on that augmenting path, and hence also for all the vertices of the graph. So in terms of distance from the source vertex, all the edges move further and further away in the course of the algorithm. And now let's look at the third lemma, lemma number 3. So that lemma said that an edge that can be removed because it got saturated in one iteration, but it cannot be removed too often. And I actually claim that between two removals of one and the same edge, okay, so we are fixing one and the same edge here, between the removals of one and the same edge, the distance labels will have decreased by at least 2. So let us look at a little example and see why this is true. So consider some iteration k, okay, where we found an augmenting path pk. Okay, so this k refers to the iteration number. And then we found an augmenting path from S to T. And the distance of this vertex here, U, was actually 7. And then correspondingly, the next vertex on this path had distance 8. Remember, that's the number of edges of the path. And in that iteration, we were saturating this edge, and therefore it got deleted from the corresponding residual graph. Now I'm claiming that when this same edge from U to V would be removed once more in a later iteration, all the distance labels, or the distance labels of these two vertices, will have increased by at least 2. Why is that true? Well, this edge got removed in iteration k. In order to be removed again, it must first come back. So that means we will have to use an augmenting path in the opposite direction from v to u. Okay? And now remember that we had lemma number 2, which said that the distance labels across these iterations, they are only monotonically increasing. So I know that in this iteration, in this later iteration h, larger than k, the distance from this vertex v from the source will be at least 8, because it was 8 before. And correspondingly, the distance of this vertex u from the source would be at least 9, one more, because the augmenting path that we now find is this one in iteration h. So now later on, in an iteration larger than h, it could be that the edge from u to v would be saturated again and will be removed. But notice that the distance label of u was 7 before. It was at least 9 in this iteration. So that means in the iteration to come, where we again remove one and the same edge from u to v, the distance label of u will be at least 9, because the distance labels are monotonically increasing. So between two consecutive removals of one and the same edge from u to v, the distance label will have increased by at least 2. Let's try to make this a bit more formal. So we consider one fixed edge from u to v, right? And we consider two consecutive removals of one and the same edge from u to v. Okay, so it got first removed in some iteration k. At that point in time, the edge was appearing from u to v. So therefore, the distance label from v was that of u plus 1, because this is the shortest path from S to T in terms of the number of edges. Now, in order to be removed again, it first has to come back. So we will have to be using some augmenting path which uses this edge in the opposite direction, right? So that is actually happening in this iteration h, later than k. And then what do I know by the monotonicity lemma number 2? Well, first of all, it holds that in this iteration h, u is the vertex that appears later, that appears after v on the augmenting path, right? Like this. And therefore, the distance of u is that of v plus 1. Now we use the monotonicity of the distance label. So the distance in iteration h is at least as large as it has been in earlier iterations, in particular in the earlier iteration number k. So that is what we use here. Okay. And now in iteration k, we actually know that the augmenting path was in this direction. So v was appearing directly after u on this augmenting path. So therefore, the distance of v was 1 more than that of u. So I plug that in, and what do I get? That I get that the distance of vertex u in iteration h is at least 2 more than it has been in iteration k, and hence, before removing in the yet later iteration the same edge once more, the distances will have increased by at least 2. So how does this help? Well, what is the maximum distance label that a vertex could actually have? Remember that we are measuring the number of edges of a path, and the maximum number of edges that a simple path can have, a shortest path can have, is n-1 edges. So there is a natural upper bound n-1 on all the distance labels actually. So n-1 is a global upper bound on any distance label. Between two consecutive removals, these distance labels increase by at least 2. So that means I can remove one and the same edge at most n-1 divided by 2 times, right? So n-1 divided by 2 is an upper bound on the number of removals of one and the same edge. So now we have proved these 3 little lemmas, and let's plug everything together to analyze the computation time of Edmonds and Karp's algorithm. So there's 2 claims. The first is about the total number of augmentations, computing augmenting paths. And I claim this is no more than n times m many. And each augmentation takes linear time in the size of the graph. This is because we just have to compute the residual graph that is possible in linear time given the current flow. And we have to compute the shortest augmenting path, shortest in the number of edges. That is just one application of the BFS algorithm, which is also linear in the size of the graph. Now, given that we have only that many augmentations, the total computation time becomes order m squared times n. So why do I claim that I only have order n times m many augmentations here? Well, that now follows from lemmas 1 and 3. Lemma 1 said in each augmentation at least one edge is removed. And how often can I remove one and the same edge? Well, at most order n times, that was lemma number 3, and hence the total number of augmentations is upper bounded by the product of the two. So for each of the edges at most order n times, that gives me order n times m augmentations at most. And claim number 2, we already argued each augmentation is a breadth first search from the source vertex, which takes linear time. So we really obtain a truly polynomial computation time for Edmonds and Karp's algorithm. And notice that in none of the arguments that I was using in order to prove these 3 lemmas, I was using the capacities of the graph. That is because we compute shortest augmenting paths in the number of edges, and that was totally independent of the actual capacities. So therefore, the algorithm and its correctness analysis works for any capacities, and not only for integer capacities. That's obviously a big improvement. And another improvement would be possible to get the computation time down to order n squared times m if you're a bit more careful with the recomputation of the residual graph and the corresponding distances. But for that, I refer you to the literature, any textbook. I'm not going to treat that now. So that finishes the analysis of Edmonds and Karp's algorithm, which has this nice computation time, which is independent of the edge capacities of the graph. And what we do next is looking at a totally different algorithm to compute the same thing, maximum flows. And that is the so-called pre-flow push algorithm. So the main difference to the other 2 algorithms is the following. So notice that for the Ford and Farquharson and Edmonds-Karp algorithm, we are always maintaining a feasible flow. In the beginning, it's a 0 flow, then it's a flow along a path, and we augment and augment. So we always have a feasible flow. On the other hand, in the pre-flow push algorithm, we start with a so-called pre-flow, which is not a feasible flow, and only at the very end of the algorithm, this pre-flow will actually be a feasible flow. So what is the definition of a pre-flow? So a pre-flow is just the same as a regular flow. It has to fulfill capacity constraints, it has to fulfill skew symmetry, but we relax the condition that the flow into a node has to be equal to the flow out of the node. So we allow that the ingoing flow is larger than the outgoing flow. So nodes may have an excess, and that is the definition. So we actually require non-negative excesses at all the nodes except for the source node. And the excess of a node, that is just all the flow going into the node U, and it has to be non-negative. So if you look at this little example here to the right, we are sending flow from S to U, but there is no flow going out of U, and hence the excess for node U would be 3. It's non-negative, so something like that would be allowed. Okay, so we allow non-negative excesses, and our earlier flow conservation constraint just would mean that the excesses at all the nodes would be equal to 0, and negative excess is not allowed. Positive excess is allowed. So inflow is allowed to be larger than outflow. Now, what's the algorithmic idea for the pre-flow push algorithm? And in a nutshell, it looks as follows. So the first step would be to push a maximum amount of flow out of the source node S. And I do that by just saturating all the outgoing edges. Okay, so this in this little example here, I have 3 outgoing edges, which have capacities 3, 4, and 2. So I would really push the maximum amount of flow that could potentially leave S into the neighboring nodes here. And that means that these neighboring nodes now would have excesses of 3, 4, and 2, respectively. Now, once I have done that, I try to transport these excesses towards the target node as much as possible. Okay, so that is what I do. I reduce the excesses or the excess of the overall flow by trying to send it towards the target node T. And as you can see here, the maximum capacity that could leave S itself was here 9. The maximum capacity here that could go into T would be 8. So there will be 1 unit of flow that cannot reach the target node. And once I have tried to reduce the excesses, I have to get this flow, this unit of flow, back into the source node. And that's also what I do. Okay. So if no additional flow can be sent to T, the remaining excess, in this example, this 1 unit, somehow has to get back to the source node. And once I have done that, I will have computed a feasible flow in the network. And well, in a nutshell, that's the algorithm. And the main question is, how do I make that happen? Okay, so what is a good way of bringing these excesses, first of all, closer to the target node, and then in the end, the superfluous excess has to get back to the source node. In order to make that happen, I am going to need 2 definitions. So the first definition is that of an active node. Okay, so that's a node that has positive excess. So that's actually a node with which we still have to do something because it has more ingoing flow than outgoing flow. And these nodes still have to be processed somehow, and we call them active. The next definition is that of a level or height of the nodes. So you should really think of these labels D now as the height of a certain vertex. Okay, so I show you a couple of pictures for that in a minute, but let's first make a definition. So given a preflow F and a level function D, okay, so F is a preflow, D is a level function, I call this level function feasible for that preflow if 2 conditions are fulfilled. First of all, the level of the source node is just fixed to be n. The level of the target node is fixed to be 0. So if you look at this little picture down here, you see a little network, and you see that the source vertex is hanging on level n, and all the other vertices are actually down there at level 0 at the moment. Okay, so the level function is called feasible if S always remains at level n and T always remains at the bottom level. So it is really how you would think of a flow. The flow is going downwards and actually trying to reach the target T, given these levels, okay? Moreover, I require that the level of a node V is at least the level of a node U minus 1 for all the residual edges. So if I have a residual edge here, actually that's a residual edge in the current residual graph. So that's an edge EF in the residual graph GF of the corresponding preflow. Then the level of that node V in comparison to node U could be, for example, larger than that of U. It could also be smaller than that of U, but not by too much. So if the level of U is actually 4, like on this picture here, then the level of V could be 3, 4, 5, 6, etc. So such a level function is called feasible for a given preflow. So once more, let's look at, say, 3 examples here. So if this edge from U to V is an edge in the current residual graph, then it's okay if this edge is downward sloping, okay, from U to V. It's also okay if it's upward sloping, but it's not okay if it's downward sloping too much. So the downward slope from U to V is only allowed to be this 1 unit here. So in writing what is a feasible level function for a given preflow? Well, as source vertex is at level n, we're trying to let the flow go out of S from level n. The target node is fixed at the bottom level 0. And then we say that, we require residual edges of the corresponding residual graph. We allow them to be falling, downward sloping, but not steeply. Okay, so they might be upward sloping, downward sloping as well, but only by 1 unit in terms of this level function. So now what's the algorithmic idea? We are always maintaining such a level function which is actually feasible, and we are going to let the flow go downwards, from higher level to lower level, and the feasibility will guarantee that flow is going downwards towards nodes which have, say, 1 level less. So therefore, we make the following definition for the operations that we're going to perform. We call an edge in the residual graph eligible if it is downward sloping by this 1 unit. More than 1 unit downward sloping is not allowed. Okay, so we will always maintain feasibility of this level function D. And the flow is going downward sloping, and such an edge is called eligible. We can use it. Now we have one operation that we're going to use. That's the initialization. And that just means emptying the source node, pushing out of the source node as much flow as possible. Okay, so more concretely, the level of the source node is going to be n. The level of all the other nodes is going to be 0, including the target node. The flow on all the edges is going to be 0 too. And for all the edges that leave the source node, we are setting the flow equal to the upper capacity. So really pushing the maximum amount of flow out of S towards the neighbors of S. And to make it skew symmetric, we also have to update the flow in the opposite direction. So that is how we start. And then we have an operation push, in which we try to push the flow from nodes with excess towards the target T. And that is this operation. It is called push from U to V. It has as precondition that the node is active. So a node that has excess can push its excess towards other nodes. And it has an outgoing edge which is eligible. So that means it's actually downward sloping. So flow is only going down the hill. What is the maximum amount that we could push from a node U to a node V via an eligible edge? That is, of course, determined by the current excess that this node U has. So in this example, that the excess would be 4. This edge is an edge in the residual graph. It has a certain residual capacity. So let's say this is 6. Then the amount of flow that could be pushed from U to V is, of course, not more than 4. Okay, so X is the amount of flow that could be pushed from U to V. And then we push it from U to V, and correspondingly, the flow in the other direction is also updated to make it skew symmetric. Now, it could also be that we have an active node. So that's a node which still has excess. Inflow is more than the outflow. We have to get rid of the excess, but there is no eligible edge. So there is no downward sloping edge from U. What do we do then? Well, the natural thing, we just hang the node U a little bit higher to possibly create eligible edges going out of U. Okay, so that's the relabel operation. So the condition is that U is active, it has excess, but there is no eligible edge going out of U, and then we just update the label. So that just means we are hanging node U 1 level higher, and then hopefully we can push the excess out of it. Now, having defined these 3 operations, I can describe the whole algorithm, and miraculously, this is going to work. So let's see. So we initialize, so that, remember, that means we are pushing the maximum of flow out of S towards its neighbors. And as long as there still exists an active node U, so that's a node which has strictly positive excess, not equal to the target node. The target node is allowed to receive flow, obviously. If I have such an active node, and if there still exists an eligible edge, then I push flow along that edge. So that is going to be in the beginning flow towards the target. If I have an active node but no eligible edge, then I relabel. So I'm hanging that node higher. And I just iterate. So I do that as long as there is active nodes. So I'm exiting this while loop here only if there is no active node anymore. And if there's no active node anymore, then there is no excess, which means flow conservation is fulfilled for all the nodes, which means we are actually having a feasible flow. And that's the flow that I return at the end. And believe it or not, this really works. So let us look at a little example how this algorithm actually works before I turn to the proofs. Okay, so here is a toy network with 4 vertices, capacity 10 and 7 out of S. Then the nodes for a change are called A and B in this example. There is a capacity of 5 here from A to B, and from A to T2, and from B to T8. So what I'm going to show in the next animation is active nodes and their excesses in blue, the level of the nodes in D. Eligible edges will turn out to be orange. And then here on the right-hand side, you will see the original network with the original capacities and the current pre-flow that we actually computed. Okay. So what happens after the initialization phase? First of all, we are pushing the maximum amount out of S. So that would be 17 units of flow. And then this one will have an excess of 10, and this one will have an excess of 7. Okay. So this is how the network looks like after this initialization phase. Notice that, for example, the excess of the source vertex is minus 17 because S is actually getting rid of 17 units of flow, right? The outflow is larger than the inflow, but that's okay. It's the source node, okay? So the source node is already hanging at level 4. That's the number of nodes in this network. All the other nodes here are currently at the level 0, so therefore there is this red zeros. Then we have an excess of 10 at this excess node A, and we have an excess of 7 at this excess node B. And here on the right-hand side, as I said, you see the current flow values and the current pre-flow. So there is 10 units going into A, 7 units going into B. So it's a feasible pre-flow because all the excesses are non-negative, but it's not yet a feasible flow. Notice also one thing, after this initialization, the labels that are defined, so having S with label 4 and levels 0 elsewhere, that is a feasible labeling of this height, or the feasible height function, because I have pushed the maximum amount from S to A and S to B. These edges are no longer present in the residual graph, only the backward edges are now present in the residual graph. And it's okay if a residual edge is upward sloping, right? These residual edges would be equal. Horizontal is what I mean. Okay, so that's the situation after the first phase, the initialization. And now what I'm going to show on each of the slides is the possible actions that the algorithm might perform and the one that the algorithm actually performs. So what I mean is the following. So what would be the first thing that could happen? We always choose an active node and try to push flow out of an active node. And if that's not possible, we would actually have to hang one of these two nodes higher. So in the very first round, there is, as you can see, no eligible edge going out of A and B, right? There is no downward sloping edge out of A or B. So therefore, the possible operations in the first round would be either to relabel A or to relabel B. And for the next slide, relabel A is the operation that we actually perform. All right, so let's do that. So that means we are hanging A a little bit higher, 1 unit higher. And that suddenly makes these two edges eligible edges, and therefore they are orange. Now, what are the possible operations that the algorithm might perform in the second round, well, there is 2 active nodes. So we could either relabel B, right, because B still has no eligible edge going out of it. If we look at A, we can push actually some of the excess out of A, either along this eligible edge or along that eligible edge to T or to B. So let's say the algorithm chooses to push along node A, B, and that's what we do. And then the situation looks as follows. So then this edge from A to B is actually saturated, and we will have in the residual graph the corresponding edge in the opposite direction. Okay. Now that's it. That was the push operation. If I go back, how did I know how much I push out of A? Well, that was determined by the excess. The excess was 10, and the residual capacity in this direction was 5. So therefore, 5 units have been pushed out of A. Okay, so that is the situation after the push has happened. Now, what are the possible actions of the algorithm? Again, I could relabel B, or I choose A as an active node, and it still has an eligible edge, so I could push flow along that eligible edge towards the target node. So let's say the algorithm pushes flow from A to T. Then the situation, how much would that be? That would be the minimum of 2 and 5. 5 is the excess, 2 is the residual capacity, so I push 2 units of flow towards the target node T. So then the situation looks as follows. The edge from A to T will be saturated, and the residual graph has the opposite edge. So now again, we are in a situation where there is no eligible edge. So we can either relabel A or relabel B. So suppose we relabel B. So we are hanging B 1 unit higher. B has moved up a little bit, which makes this edge suddenly eligible. So the possible operations would be relabeling A because it's still active, or pushing out of B because it has an eligible outgoing edge. So let's say the algorithm pushes along BT, so out of B. After that, the situation looks as follows. None of the edges going out of A and B is eligible anymore because both edges are saturated. Notice that the target node is already receiving 10 units of flow, which is going to be the maximum flow value. So in the remaining iterations, the only thing that the algorithm has to do actually is to get rid of these excesses and get them back towards the source S. And we already know, if we look at the network, there is a network cut here, which has capacity 10. So 10 is the maximum flow value. So let us just see how this happens using the operations that we defined. Okay, so in this phase, we can relabel any of them. Say if we relabel A, so A will be a little bit higher, nothing happens. So still no eligible edges. So let's say then we relabel B. Okay, B is moving higher, still no eligible edge. So let's say we again relabel B. So B moves a little bit higher. And then what we observe is that there is now an eligible edge from B to A because B has level 3 and A has level 2. Okay, so we can push along this edge. So let's say the algorithm does that. So we push along the edge from B to A. How much? Well, that's 4 units sitting. That's the excess of B, and 5 is the residual capacity. So 4 units would go to A. That's what we do. And that is what the residual graph looks like after we have done that. Notice that B is no longer active because all the excess flow in B was actually pushed to A, and all the excess is now sitting in A. As A is the only active node, we have to relabel it, and that's what we do. We see that nothing happens, so we moved it from level 2 to 3. It has level 3. B also has level 3, and the source node has level 4. So A is still the only active node, so we have to relabel it again. And now we see that we can actually push flow from A to B. Okay, so that is not strictly necessary, but it might happen. So we do that. Let's say that is the only option that we can do at the moment because the edge towards S is not yet eligible. Okay, so we push flow from A to B. That's what the algorithm does. And then we again have an excess of 3 at B and an excess of 4 at A. We have 2 active nodes again. That, by the way, shows also one thing. The number of active nodes is not monotonically decreasing in the course of the algorithm. So we have 2 active nodes again. We can relabel any of them. Let's say we relabel node A. And then finally, A is hanging higher than S. So the level is 5 here and 4 there. Okay, and then these 3 units of flow can be pushed towards the source. So we do that. No, sorry, the slides are suggesting something else. We don't do that. We first relabel B. So there is 2 possible operations again, either pushing out of A or relabeling B. And my slides suggest that we are actually relabeling B. So we do that. B moves from level 3 to 4. There is again 2 eligible edges, pushing out of A or relabeling B once more. Say we relabel B once more. Let's do that. And now both A and B are on level 5. The source node is on level 4, so both nodes can actually send their excesses back to the source. And let's say we first push along A and S, so sending 3 units from A to S. That means A has no excess anymore. B is the only active node. Now we push from B to S, these 4 units, and we are done. There is no active nodes anymore in the network. And when we look at the picture on the right, we also see that we now have a feasible flow. Inflow, positive inflow is equal to positive outflow at the 2 intermediate nodes A and B. So as there is no excess in the network anymore, except for the target node, of course, no more operations are possible, and we stop with a maximum flow. I guess you must have noticed that I mixed up the excesses with a label at one point in my description of the previous example. Sorry for that. So the algorithm works for this example, obviously, but we have to formally prove its correctness. And also I want to make a claim on the computation time. So I start with this lemma, which says that at least at any point in time, the algorithm maintains a feasible preflow F and also a feasible labeling D. So let's see why this is true. It's an inductive proof on the number of iterations of the algorithm. So the first step is going to be making that claim after the initialization phase. So in the initialization, we are pumping all flow out of the source vertex into all its neighbors. So certainly the corresponding flow is a preflow because all the excesses are non-negative except for the source vertex itself. But does it also have a feasible labeling? And the answer is yes. And that has to do with the fact that we are pumping everything out of S, right? So that means in the residual graph, none of these edges out of S are present. Only the opposite edges are there. S is the only node with the label N, and all the other nodes have actually label 0. So that means that, remember what it means to be a feasible labeling. That means that, well, source vertex should have label N, target vertex should have the label 0, and all the edges in the residual graph are either upward sloping, and if they are downward sloping, not by too much. And since we only have horizontal edges here in this part of the graph, and these upward sloping edges, we are fine with respect to the feasibility of the labeling after the initialization. So inductively, we assume that the claim or the lemma is still true after an iteration I, and we are considering the next iteration I plus 1. So we have two operations that we're actually performing. One of them is the relabel operation. Well, first of all, if we relabel, the flow remains unchanged by definition. But do we also maintain a feasible labeling after the relabel operation? Let us have a look. So when we actually relabel, we are relabeling an active node, so a node with positive excess, such that none of the outgoing edges is eligible. So before this relabel operation, the labeling was a feasible labeling, so that means all the edges were downward sloping. And since no edge was eligible, this is not fulfilled with equality for any of the outgoing edges. So this is so the label of V must be strictly larger than the label of U plus 1. So we know that D of V is actually strictly larger than D of U, sorry, minus 1. Okay, so that means the situation looks as follows. We have U here. The label of V could, for instance, be equal to the label of U, still fulfilling this inequality, but it could also be larger, right? All these would be possible options. And in all these situations, it's totally okay and maintaining a feasible labeling if we increase the label of U by 1 unit. So the relabel operation maintains feasibility of the labeling. So we are fine with the relabel operation. Now let us have a look at the other operation that we are actually performing, and that is the push operation. Well, first of all, if we push from U to V, we maximally push the excess of U into node V, or maybe less. So that means the flow still remains a pre-flow because there is no chance that we will create a negative excess anywhere. So again, we will have to verify that after the push, the labeling is still a feasible labeling. So if we push, two things can actually happen. Edges could disappear, but that doesn't hurt because then we don't have to prove feasibility of the labeling for that edge that just disappeared. So that is certainly fine. So if we saturate an edge, a saturating push, then there is nothing to prove for the vanishing edge from U to V. But on the other hand, when we push, it could be that the edge in the opposite direction actually shows up in the residual graph. And we have to verify that the labeling is feasible also for that new edge that might appear in the residual graph. So let's have a look at the push operation. So when we push from U to V, that means we are pushing at a downward sloping edge, right? And possibly this new edge from V to U appears in the network, but we know that the label of V is exactly one less in comparison to the label of U at the push operation. So as I said, when the edge from U to V actually vanishes, nothing is to prove for that. But what for the other edge? What we need to show for the other edge is the feasibility of the labeling. And that now means that the label of U should be at least D of V minus 1. But what we actually have, because we pushed only in this situation up here, what we have is even more. We know that D of U is equal to D of V plus 1. So we are fine. So also for the new edge that might appear in the residual graph, the labeling remains a feasible labeling. So we are also fine with this case here, and hence in both cases, the labeling remains a feasible labeling, and the lemma is proved. So the algorithm always maintains a feasible labeling and a preflow F. Now the next lemma links the existence of a feasible labeling to the existence of augmenting paths in the residual graph. So the statement is as follows: if we have a preflow F for which a feasible labeling actually exists, then there does not exist any augmenting path in the corresponding residual graph. And you see the connection to the optimality proof that we actually need, namely non-existence of augmenting paths. So why is that true? Okay, So let's have a look. Suppose there exists an augmenting ST path in the residual graph. Certainly such a path has no more than n-1 edges. But now we have a feasible labeling D, and that means that all the edges in the residual graph are possibly downward sloping but not too much, or upward sloping. So if I look at the augmenting ST path, it kind of might look like this, with downward sloping edges, but along the path, or along any edge that lies on this path, the label of V is at least the label of U -1. So it's not too much downward sloping. We know that the label of the source vertex is N, and the length of the path is at most n-1 edges. Hence, because of this inequality, I immediately get that the label of T must be larger than 1, which is n-1. And that's a contradiction because a feasible labeling requires d of t being equal to 0. So here is the summary of that argument in writing. And that actually has a strong implication because this is a lemma for a preflow, and we are maintaining a feasible labeling at all times during the algorithm. Okay, so that means at all times there does not exist an augmenting path in the corresponding residual graph. So that actually means the following: once our preflow becomes a flow, so once all the excesses are gone, this is already the optimality proof because we have no augmenting path anymore in the residual graph, right? So this algorithm actually does the following: it maintains optimality at all times, because this optimality proof is valid throughout the algorithm. Only the optimality proof is not for a flow, it's only for a preflow. So we are maintaining optimality at all times, and in changing the preflow to a flow in the end, only at the end of the algorithm we get feasibility. So we are optimal all times, and at the end only feasible. So that in contrast to the other algorithm by Edmonds and Karp, where we maintain feasibility at all times, and at the end we obtain optimality. So just to summarize that in another lemma, so in this preflow push algorithm, once it terminates, it actually terminates with a maximum ST flow. And that is true because the termination is triggered by the fact that there is no more active nodes. And that means our preflow has turned into a flow, right? So if the algorithm terminates, we are having a flow. And then the previous lemma is immediately the optimality proof for that flow. Since the previous lemma exactly implies that we do not have any augmenting path anymore in the corresponding residual graph. So once again, if the algorithm terminates, then it does so with a maximum flow, and we are fine. So the final ingredient for the correctness of this algorithm is the proof that it actually terminates. Okay, so why doesn't it push around the flow forever in the network? And for that, we need this final ingredient, the final lemma. The algorithm must actually terminate because we have at most order n squared times m push and relabel operations. And that also immediately shows that the computation time is order n squared times m, because a push operation is a constant time operation, and so is a relabel operation. Now, the proof of this final lemma on the computation time is actually a nice one because it uses a new technique that we haven't used before, and that is the idea of using a so-called potential function. And it goes in a couple of steps. So the first step is actually showing that at any time the label of any node u is upper bounded by 2n-1. And how do we show that? Well, we show that actually by showing that there always exists a path from u to s when u is actually an active node. So for all the active nodes, and remember that's the nodes that have a positive excess, there always exists the possibility of sending that excess back to the source vertex S. Now let's see why this is true on the next page. So we fix a vertex U, an active node U, and we define T to be all the vertices that are reachable from U in the current residual graph GF. Okay, so we have a vertex U with positive excess, and several vertices are reachable from U in the residual graph, and the set T is everything that is reachable from U in this residual graph. Okay, so there is some excess present in this set T, at least here at node U, but maybe at other nodes as well. So the total excess that is present at the set T here, that must have gotten there, and it must have gotten there through sending flow from the rest of the nodes into T, right? So the total excess that is present in the set that is equal to the flow into T. That is by definition. Now, the next observation is that by definition of T, this edge from V to W is not present, because otherwise W would be in T, and this is not the case. So this edge is not in this residual graph, which means we cannot have positive flow in this opposite direction from W to V. If we had positive flow in this direction, this edge would be there in the corresponding residual graph. So that means that the flow value from W to V, is smaller or equal than 0. Okay, and that is true for all the edges that are pointing into the set T. So for all the edges into T, the flow value is smaller or equal than 0. Once again, otherwise the corresponding residual edges would be there. So that means that the total flow into T is smaller or equal than 0. Okay, so the total flow into T, but that is the sum of the excesses, and we know that this comprises at least one node with a positive excess. So if it contains at least one node with a positive excess, and the total excess is non-positive, it must contain a node with a negative excess too. But the only node with a negative excess is the source node S. So actually we have proved that S is in T. So that means actually that there exists a path in GF from U to S. And U was a vertex, an arbitrary vertex with positive excess. But once again, if there exists a path from U to S, actually, from U to S in the corresponding residual graph, then again, the length of such a path can be no more than n-1 edges, and each of the edges may be downward sloping, but not too much. And now the same argument again. The label of the source vertex was n by definition, and hence because the length of this path is at most n-1, what could be the label of this node U maximally? Well, d of U could be maximally d of S plus n-1, which is equal to 2n-1. And that's exactly what I wanted to prove. So indeed, we have shown that at any time during the algorithm, the label of any node U is at most 2n-1. You might have noticed that we argued only for active nodes, but the claim is actually written down for all nodes in the graph. But notice that the label is only changed for active nodes. So in the beginning of the algorithm, all the labels are equal to 0, and the label gets only increased for active nodes. Hence, it is sufficient to prove the claim for active nodes, and then it will automatically also hold for all nodes of the graph. So since the labels of all the nodes are upper bounded by 2n minus 1, how many relabel operations can we actually do? Well, obviously that is going to be at most n times 2n minus 1, which is at most 2n squared relabel operations. The next step is going to be upper bounding the push operations, and that is a bit more complicated. And we do the following trick. We split up the push operations in the saturating and the non-saturating push operation. So the saturating push operations, that's those operations where we actually saturate an edge, which then disappears from the corresponding residual graph. And the non-saturating push operations are the ones where this is not happening. So the first claim is about the saturating push operations, and I claim that in total, we have at most n times m saturating push operations. And the argument to show this actually reminds very much of the argument that we used earlier in order to show the computation or derive the computation time for the Edmonds and Karp algorithm. Because the trick is showing that between two consecutive push operations for one and the same edge from u to v, the corresponding label must have increased by at least 2, and then we know that the label is at most 2n minus 1. So we consider one fixed edge from u to v, and we consider a saturating push operation, which means this edge from u to v is going to be saturated. So let's have a look. So we have a push operation here. We are pushing from u to v, and the corresponding edge gets saturated, so that means it will disappear from the corresponding residual graph. So the same edge can be used again for a saturating push operation only when it came back. So since this edge disappeared, it must first come back. And in order to come back, we have to push from v to u in a later iteration. And at that point in time, node v is already 2 units or has a label 2 higher than at this iteration here. And then at yet another iteration, we can push from u to v actually. And again, since the labels never decrease, they are only increased in the course of the algorithm by definition, the label of u for the saturating push from u to v, so in the same direction, can only happen if the label has increased by 2 units. And now since the label of u is upper bounded by 2n minus 1, we can actually push from u to v, saturating edge uv at most 2n minus 1 divided by 2 times. And that is obviously at most n. So each single edge can undergo at most n saturating pushes. So in total, we have at most m times n saturating pushes. Okay, so that means we are also fine with the third statement here. So we have an upper bound on the number of saturating pushes, and the only thing that is still missing is an upper bound on the other pushes, so the non-saturating pushes. And in order to get this done, we actually relate it to the saturating pushes and to the relabel operations by the following trick. So we define a function phi, which is called a potential function, and it's the sum of all active nodes u, and then I just take the label of that node u, okay? And I look at the development of this function phi in the course of the algorithm, right? So this whole sum, it could go up and down in the course of the algorithm, depending on the labels of the nodes u and depending on which nodes are actually active and not. So remember what we want to do. We want to get a handle on the number of non-saturating push operations in the algorithm. So the first thing to do is to figure out what effect a non-saturating push operation will have on this function phi. And for that, let's have a look at the function. So here's the definition of the function again. So it's the sum over all active nodes, and I just take the corresponding label of that node. And notice that in the course of the algorithm, it can actually be that nodes enter this summation here because they become active and weren't active before, and nodes can leave the summation because they become inactive. So as I said, we first look at the non-saturating push operation. So push operation always goes downward sloping, and non-saturating push means that we are sending the excess of node U into node V, and non-saturating means that the residual capacity of that edge in the residual graph is not reached. So we are sending less than the residual capacity. And that means that this node, which was active before, will become inactive. So therefore, this node U leaves the summation in phi here, and the corresponding function phi drops by the corresponding distance label or label of U. Of course, since we are sending flow from U to V, it could be that V wasn't active before and now becomes active. So therefore, this node U, V could possibly enter into the function phi. And then the function phi increases because we now have to consider node V as well. By much does it increase? Well, at most the label of V. Why do I say at most? Well, because V could have been present before in the summation, but maybe not. And the label of V is exactly the label of U minus 1. But that means that the function drops because U drops out of the summation. The function might increase, but at most one less. So there is a net decrease in the function phi of actually 1. So that's the trick. Whenever I have a non-saturating push, this function phi decreases by at least 1. And now I just have a look at all the other operations that we are doing and what the effect is on the function phi. So what about the saturating pushes? Well, if I have a saturating push, that means that I saturate such an edge, and that could actually mean that node U remains active and was active before, so we don't have the drop, and V becomes active, so there might be an increase in the potential function, but this increase is at most the label of V, which is upper bounded by 2n minus 1. So the saturating push could let the function phi increase by at most 2n minus 1. Next, what about a relabel operation? Well, by definition, we are relabeling a node, so that means we are increasing, hanging this node 1 higher, so the increase is exactly 1. Now, in order to finish the argument, I have to know what the value of the function is actually in the beginning. In the beginning, this potential function, and that's my claim, is equal to 0. Why is that? Well, because all the active nodes, that is all the neighbors of the source vertex S, they actually have a label equal to 0. So we are summing a couple of zeros here, and hence the whole function is equal to 0 at the initialization. So now what do we have? Well, we have a couple of possibilities for this function to increase from 0, and that is the saturating pushes and the relabel operations, and the non-saturating pushes are actually making this function decrease by at least 1. So therefore, let me just sum up the total increase that could happen in the course of the whole algorithm. Well, that's going to be 2n squared for the relabel operations. Why was that? Well, each vertex can have as maximum label 2n minus 1, so that makes n times 2n minus 1, so at most 2n squared, and each time the function increases by 1. So that gives me this 2n squared. And now we argued that we have at most n times m saturating pushes. That was one of the earlier steps of the proof. And each saturating push lets the function increase by at most 2n minus 1, namely when this vertex v enters into the summation. And that is at most, in total, that is at most 4 times n squared times m. And that is actually what I wanted to prove, because now the total increase of this function phi caused by these two operations is at most 4n squared times m. And hence, since each non-saturating push lets the function decrease by at least 1, we can have no more than that many non-saturating pushes simply because the function by definition always stays non-negative and it starts out at 0. So now we are in shape, since we have just also argued that the number of non-saturating pushes can be upper bounded by a polynomial function. And well, this is the largest of all these upper bounds. And then in total, the total number of operations that we are doing, so relabel saturating pushes and non-saturating pushes, cannot be more than this order of magnitude, order n squared times m. So the algorithm does terminate after a polynomial number of steps. And therefore, since we know when it terminates with a maximum flow, this finishes also the correctness proof of the algorithm. This also finishes the algorithms for maximum flow problems. And let me just announce that the next lecture is actually going to be about matching problems. And we are looking at Edmond's famous algorithm for matchings. Thank you for your attention.